Well, howdly doodly, neighbor. It's great to see you all again. I guess I'm not seeing you. I'm more knowing that you're there. You're out in the ethereal presence. Um, Today I'm going to start the second part of Unit 6. I'll call it Unit 6B. If I was smart, I could have just called it Unit 7, but it's too late now. I already put it in the paperwork. Why is it writing so small? Make this writing bigger. Anyways, what the second part of Unit 6 will be dedicated to is a few different topics. One, we'll learn about something that I believe you've learned about before, um, the Pythagorean Theorem, and we'll use that to develop some special relationships, particularly called special right triangles. And there's two different types of special right triangles that we'll study specifically. One is called a 45-45-90 triangle, and the second one is called a 30-60-90 triangle. And those values refer to the angle measures of each of the angles in a triangle. Um, the second part of Unit 6, Unit 6B, Part B, if you will, is dedicated to talking about some properties that have that we can deal with functions, and it's really not connected to the first part of the unit at all. Um, oh, I forgot one topic before talking about that stuff. Right triangle trigonometry. Prior to learning about that function stuff, we'll learn about this notion of right triangle trigonometry. Um, and right after that, we will learn about some particular ways that we can perform operations on functions. Um, like if I'm given two general functions out of the blue, any of the functions that we might study, um, then um, what are some things that I can do with them? I can add, I can subtract, I can multiply, and I can divide those functions. But turns out there's one additional operation, well, I guess a few, but one additional operation that we'll call composition that we'll study in that part of the unit. And we'll use that to introduce a particularly nice thing that you'll see a lot in calculus, but we introduce it in Algebra 2 called the difference quotient. So really the second part of Unit 6 is all dedicated to really these 5 topics. And you'll have a quiz at some point over the first 3 and then over the second 2. I haven't decided how I'm going to administer that quiz, but it is what it is. Today, this video, though, is really just dedicated to making sure that we're clear on the Pythagorean theorem. That if I know that I have a right triangle, or right triangle being a triangle that has a right angle in it, or a 90-degree angle in it, then there's a relationship between what are called the legs of the right triangle and the hypotenuse. Just for some vocabulary, the legs of a right triangle, they don't always have to be the same length. I don't know why I drew it that way. The legs are the sides that are not the hypotenuse, and the hypotenuse is the side that is opposite the right angle. So every right triangle has 2 legs and 1 hypotenuse. Not every triangle has a hypotenuse, just right triangles. What does the Pythagorean theorem say? If a right triangle has legs of length A and B and a hypotenuse of length C, then a squared plus b squared is equal to c squared. That's how you often hear it. Really what it's saying is that if I take the sum of each of the legs, square them individually, and I should get the hypotenuse squared. Um, so let's utilize the Pythagorean theorem. Just as a thing that you should note for the Pythagorean theorem, the hypotenuse will always be on the side by itself in setting up the Pythagorean theorem. So in this first example, triangle DEF has sides or legs of length 5 and 12 and a hypotenuse of length c. That's what we're solving for. If I'm setting up the Pythagorean theorem, then that would be 5 squared plus 12 squared is equal to c squared, or that 25 plus 144 is equal to c squared, meaning that c squared is equal to 169. Now from here, we know that in order to find the value of c, I need to apply the square root operator on both sides of the equation. What that means is that I'll get a value for c. Theoretically speaking, I should include both plus or minus 13 as numerical solutions to this equation, but in the case that we're dealing with a geometric example like a triangle's side length, you don't have to include the negative solution, just because it's something you'll learn that that triangles can't have negative side lengths, that the side length will always be a positive value because it represents a distance. So here, what this tells us is that the hypotenuse has a length of 13 in whatever unit is listed here. If there's not a unit listed, you don't have to include a unit. If there is a unit listed, then you do have to include it. The second example is very similar. I set up the sum of the two legs squared. I'll use a different color, why not? 10 squared plus 5 squared is equal to the hypotenuse squared, or that 100 plus 25 is equal to c squared, meaning that c squared is equal to 125. In this example, it is assumed and generally speaking will be stated that all of your solutions need to be stated in simplest radical form. That's why we studied radicals. So in solving this, I know that c is equal to the square root of 125. I need to state that in simplest radical form, meaning I need to pull out any necessary factors under the radical that I can. 125, as a side note, just happens to be equal to, come on, pen. Pause.